So how is everyone today? Awesome. So my name is Emily, and for this talk, Dissecting Git's Guts, I'll be doing a deep dive into how Git works under the hood. But before I begin, I wanted to get a show of hands. How many of you here use Git on a daily basis? Right, most, if not all of you. So I really like teaching this topic because programmers use this tool all the time, but most have a rather superficial understanding of how it actually works. So I think you've seen this comic once before tonight, but XKCD makes a pretty funny joke of this, of how for most people, Git is complete sorcery. And because of that, they are kind of left in the dark once they screw something up, right? So how many of you have had something go terribly wrong in Git? Yeah, I believe there's a term for that. Git happens. Fortunately, knowing what goes on under the surface empowers you, as it leads to a better intuition and thus a better ability to navigate the system once something goes horribly awry, or just even in everyday usage of the program. So that's what I hope you walk away with from this talk tonight. More comfort in using Git and a better conceptual understanding of the system. For example, what is at the heart of a branch? Or what is happening when you are doing a Git checkout? Or what is a detached head state? And the way I'll approach this talk is with the assumption that you are familiar with Git porcelain commands. This is the term for all of the high-level commands that you as an end user interface with on a daily basis. So, git push, git pull, git log, git merge, and so on and so forth. And while we're on the topic of terminology, on the flip side, you have something called Git plumbing. And we're not talking about toilets here. Plumbing is the term for all of the low-level commands that allow you to manipulate, inspect, and compare the basic structures of Git. And we'll use these plumbing commands as a tool to sort of poke around and dissect how Git is fundamentally structured. And this is how we're going to do it. First, we'll talk through the concept of the .git folder, which is where the Git magic happens. Then we'll drill in and look at the objects directory, which is where Git stores stuff. We'll later move on to the refs folder to explore how Git aliases things. And lastly, we'll take a look at Git pack files, which is how Git saves space and how that sort of ties into the system's general structure. Sounds good? Great. So let's walk through the Git internals from the ground up, starting with what makes a Git repository. And I'm going to go create a folder, and I'm going to go into it. And I want to run a number of Git commands on it, like git log. But even though I have Git installed on my machine, I can't do it yet. And if I try, I get a fatal error. That's because before you can perform project-specific Git operations on a folder, you actually have to initialize Git. And the way you do that is through a porcelain command. Does anybody know what that command is? Git init, yes. So this puts into place the scaffolding that Git needs to operate on that project. Great, so now it tells me there's a Git folder that's been created. But if you run an ls on it, you don't really see it. But actually, let's do an ls-la, which shows the hidden folders and files in a directory. L standing for list format to make it look pretty, and A to show all of the files. And there you go. Now you can see it. The very bottom one. There it is. So the .git folder is what makes a directory a Git repository. It's where everything that Git stores for a project lives. And because of this, if you ever wanted to back up or duplicate a Git project, you can simply just copy over this hidden folder, and you'd have all of the history intact. In fact, when you run a Git clone from a repo from a remote source, like GitHub or GitLab, that is essentially all that you are doing, copying over the .git folder. So now it makes sense that the .git folder would be hidden to begin with, right? If this folder contains all of the vitals, you typically don't want people tinkering around with it. But we know what we're doing, so let's run an ls to see what Git guts are made of. Cool. So the parts we're concerned about for this talk are the objects folder, refs folder, the head file, as well as an index file that has yet to materialize. So these 4 things constitute the heart of Git's structure. The rest of it is either just personalized configurations or user-defined scripts that are beyond the scope of this talk. Who has gone into the .git folder, by the way? Awesome, a room full of intrepid explorers. Well then, let's go spelunking, and let's examine this folder to see what it's all about. We'll start diving into the objects directory. You might wonder, where does Git keep all of the different versions of my files, all of the content? And the answer is right here, in this objects folder. This is just a folder which functions as Git's database. And the term that you can use to describe how this database works is content addressable file system, which is essentially just a method of storing information so that it may be retrieved based on content. So let's do this. Let's put an object in the Git database. I'm going to go ahead and write a file, hello world, because why not? Fill this up with hello world. I'm going to save this. And now we're going to use a plumbing command called git hash object that allows us to copy over this file into our objects database. The W here indicates to Git that you want to write it. And we pass in the name of the file that we want to store. And great. So now we get back this hash, this weird-looking string of gibberish comprised of 40 hex characters. And in your time using Git, I'm sure you've run into these. Who's seen these? Yeah, we've all seen them. Git log is probably the example that you're thinking of. So this hash is generated by the SHA-1 algorithm, which is built into that hash object plumbing command we just used. And the hash it produces is, for the most part, uniquely generated based on the contents of a file. To drive home my point, I'm going to run the raw SHA-1 function on this content on my command line to see for ourselves. And we prepend some metadata, file type and size, to match the fact that Git hash object automatically does this for you right before running SHA-1. And that's just to escape the bang character. And here's your command. And voila. For any given set of content, you will always reliably generate the same hash key. And you can do this really any number of times, and you're always going to get the same hash back for this content. However, if you alter the content in any form, I'm just going to go in and I'm going to change this. I'm going to add like an S to hello world. You'll notice that you'll get something drastically different back. So getting a hash that uniquely matches with a set of content, kind of in the way that a fingerprint is a unique identifier for a person, this concept is super important, as it's at the heart of what makes it a content addressable file system. Anyway, this hash can now be used to retrieve the content that we have saved in the objects folder. And by the way, this is where we have saved it. I'm just going to show you. And it's organized such that the first 2 hash characters creates a subdirectory under the objects folder, and the remaining 38 functions as the file name. And we can retrieve the contents by using the plumbing command git cat file, which allows you to inspect any Git object. The P flag here stands for pretty, as in readable format, and we pass in the hash of the corresponding object. And there you go. There are the contents of the file. But actually, if you try to read it like any other file, if I try to cat it, you'll see that what you get back is entirely gibberish. So the files that Git saves into its database aren't just stored as raw copies of what you have. That makes no sense. If you think about the fact that Git has to operate on potentially massive code bases, I think, for example, of my previous company, which had repos with hundreds of thousands of lines of code and just thousands of files, it would not be scalable. Rather, the contents are compressed into these smaller objects, and zlib is the compression library that they use. So now that you've witnessed how Git stores our files, let's play around with some versioning. I'm going to go ahead and edit this file to make version number 2. I'll open it up in Vim. I'm just going to add another line. I'm going to add the world is beautiful, because it certainly is. I'm going to save that. And now if I run the hash object command on it, pass in the W flag once again to write it, pass in the name of the file, you'll see that what we get back is a different hash, as you can expect. So now if we show the contents of our objects folder, and I'm just going to use a shortcut here for that find command, you'll see that there are now 2 Git objects stored in the Git database. And if we open this object that we just created, what you see might surprise you. So it's the newest version of our file in its entirety. I taught a workshop version of this talk at my previous company, and in that time, I found that consistently, developers tended to think that version 2 of a file in the objects database would be a diff off of version 1. I think some other version control systems, like Subversion, stores diffs. But Git is a different animal. For each version, it stores an entirely different copy of your file, initially. There was, however, a follow-up to the statement, but we'll get to it a little bit later on in the talk. So another thing to note is that Git uses the hash to detect when a file has changed, and will thus be more selective of when to store a new object. So if you try to store a file that is exactly the same, line for line, character for character into your objects directory, it will detect that it already exists, and it won't duplicate it. But it will spit back at you the same hash, as you see here. And this is true if you saved a dozen files with a different name into your database. And that is part of Git's beauty. It's pretty space efficient in the way that it's designed. So anyway, this type of object that we've been talking about has a very specific name. I briefly mentioned it before, but for demonstration purposes, we can use the plumbing command cat file to inspect the object. And this time we'll pass in the T flag so as to indicate that we want to know the type. And there you go, blob. So that's the name of this object that we've been creating and looking at and inspecting. And blobs are important because they are the primary object store containing all of your file content. But you might have noticed that when we looked at these blobs, they are literally only your file content. So how do we know what file name this blob goes with? Or how does Git represent saving multiple copies of a file under different names? And more importantly, what if we want to group a bunch of files together to create a snapshot? Because that's what Git is, right? It's not just a snapshot of one file, but your entire folder at any given point. So there's another type of object for this that gives us this layer of information that we're looking for, and it's called tree objects. So whereas blobs correspond to your file contents, well, you can think of tree objects as a complete snapshot of your project directory. So we're going to make a tree to demonstrate. But first, we need an index file, because that's what Git makes trees from. So you might ask, what is an index file? Well, actually, you know what it is because there's a user-friendly metaphorical term for it that you see all the time. And it's called staging area. So to move forth, let's first stage some files, aka putting stuff into our index by using the plumbing command, update index. So the add flag specifies that we're adding to the index, and we pass in the name of the file that we want to stage. And actually, I'm going to go ahead and add yet another file into our index. I'm going to create one, foobar. I'm going to open it up. I'm going to write some gibberish. Very meaningful. And I'm going to save it. And this time, I don't actually have to manually call hash object beforehand because update index has that functionality built into it. If the blob isn't already there in the objects database, it will automatically be added under the hood. And now, if we look at the .git folder, we see that we now have this index, which wasn't there before. And if we inspect the contents of the index with the plumbing command git ls files, you can now see that it is a running list of the stuff in our staging area. So under the hood, that's all your staging area really is. And if you run a porcelain git status, there we go, you'll see that we have indeed added stuff into our staging. So by now, we've saved files into the Git database, and we've updated our staging. And you've probably already guessed which porcelain command we've effectively mimicked by using low-level plumbing. What is it? Git add, that's right. So now that we have an index for the tree object to base itself off of, let's go ahead and finally write that tree. And as you'd expect of all objects you write to the object folder, you get back a hash. Let's examine it. We'll use the cat file command, pass in p for pretty. And there you go. So this is what a tree object looks like. And you'll see that it contains the file mode, the object type, a reference to the SHA hashes of the blobs along with the file name. One thing to note that isn't being shown here, by the way, is that in addition to pointing to our blobs, trees can also reference other trees too, so as to illustrate this notion of subdirectories. And if you were paying close attention, you might notice that this tree object, in fact, looks exactly like the index file that we just looked at, right? And that's absolutely the case, except that unlike the index file, which is meant to be in a constant state of flux because it is your staging area, the tree object is a finalized snapshot, captured and persisted into your Git database. And you can see that this is the case here, because when you list this, all of your objects, we now have another item in there. So now it's official. We now have a snapshot of our current working directory stored in our Git objects folder, but it seems like we're still missing a little bit of metadata here. You don't have any information about who saved these snapshots, what time they were saved, or why they were saved. So enter the concept of the commit object, which takes care of all that. So anyway, let's go and create a commit object. We'll use the plumbing command commit tree for this. We'll pass in the SHA hash of the tree object. This is the one that we just made. And like with all objects that we've dealt with so far, we get back a SHA hash, and Git predictably sticks it into the objects database, as you can see right here. And if we take a look at it, we'll see that what you get back looks like our typical commit. This is pretty familiar, right? So very importantly, at the very top, we have the hash of the tree that this object points to. We have the author, that's me. We have the committer, that's also me. And then we have the timestamps. And then the all-important commit message. By the way, that is a terrible commit message. I hope your commit messages are a lot more descriptive than this. So I'm just going to take a drink of water. So as of now, by writing a tree and creating a commit object, we've effectively mimicked a porcelain Git commit. So let's put another commit on top of this one, because I want to demonstrate how Git relates commits to one another. So let's say that I'm editing this foobar file for this commit. I'm going to go ahead and add some more lines of gibberish here. Save that. I'm going to update my index again. I'm going to write this tree. And then I'm going to create a second commit. So here I'm going to. So here's the hash of the commit. Of the tree that I want to make a commit out of. And here I'm going to chain the commits with this p flag. P standing for parent, telling it to link this commit to a parent commit, the one that came before it, so as to indicate this sense of hierarchy. And we get back a hash as we expect. So let's take a look at this commit object. And it looks pretty similar to the previous commit. But notice, in this one, there is now actually an additional line in there, one that says parent, along with the hash of the previous commit. So now, if you run a git log on this specific commit hash, there you go. Then you'll see how by simply chaining these commits, we're starting to build up a history. So there you have it. You've performed a low-level git add and git commit. And if you were following along, you probably noticed the tree-like way that Git is structured. At the very lowest level, we have the contents of our files, which is the blob. And each revision is a different blob. And then you have another layer built on top of that in order to associate these files in a snapshot, which is the tree object. And then on top of that, we have yet another layer of metadata, the commit objects, which are then chained to one another for the purpose of forming a history. And everything is chained in one direction by the usage of hashes to point from one node to the next. The children always knows its parents, but never the other way around. And if you drop anywhere on this chart and follow the pointers, you'll never end up back where you started. Thus, it is a DAG, which is a directed graph that contains no cycles, directed acyclic graph. And these hashes are generated based on the file's contents, which in turn, as you saw, contains the hash of any preceding nodes. This creates a chain of dependencies in which the hash of each subsequent object depends on the one before it. In this way, Git is also structured as a Merkle tree. And as it's both a DAG and a Merkle tree, some like to call it by the hybrid name of Merkle DAG. Regardless of what you call it, you can start to see what sort of advantages this structure might hold. For one, because of the hashing, in that the key is uniquely generated based on the contents, you can verify that the data you put in will always be the data that you get back out. It's a way to maintain data integrity. If there's any corruption, Git will absolutely notice it. At the same time, it allows for any sort of deduplication of any common children, which I demonstrated at the blob level. And for another, it makes for a highly flexible, lightning-fast piece of software, given that we can content address any of the nodes in the data structure. You have all of the content, and it's just a matter of pointing to it via the hashes. Which brings us to our next point, which is references. So now, we know how Git stores our information in 3 primary object types: blobs, trees, and commits. And it's kind of all actually just floating around in the objects directory. They're not organized by whether it's a blob or a tree or a commit. But when we work with Git, how do we keep track of what commit we work off of? Well, usually we're working with branches, so there's our answer. But what exactly is a branch? And how does Git know what objects go with a given branch? So the answer is it's pretty simple. Branches in Git are merely aliases, or pointers, to the commit objects. And these pointers reside in your refs heads folder. Refs meaning references, and heads meaning the top-level commit for a given alias. So this directory should contain a running list of all branches that are in this repository. We listed it, but there's nothing there so far. That's because we don't have any branches yet. But let's change that. We can use the plumbing command git update ref to do so, and we pass in the name of the branch that we want to make, master, and the commit that we want to point it to, which was the last commit we just made. And now, if you list your ref's heads folder, you'll see that you now have a master branch in there. And if you open this guy up, there, you'll see that all that really is to it is just a text file. I could cat it. It contains a hash of the commit object that this branch points to. So in effect, what we've done is this. We just created a reference to the commit. And that's all there really is to a branch, really. Now, oftentimes, when you're working in Git, you're branching off of master. So let's try that. Let's branch off of master and see what happens. We made a feature branch. And now if we list the ref's heads folder again, we'll see that we've now created another reference in the heads folder. And if you open up this new branch to see the hash, we'll just cat it, because it's not an object. You'll see that the hash for this branch is exactly the same as the one for master. So effectively, we've created two references into the same commit. And visually, it looks something like this. We just added a new branch for the same commit, right? So that's all that happens when you freshly branch off of master. But let's say that we've edited some files and then added a commit on top, because this is what we normally do when we're working on a new feature branch, right? I'm going to edit the hello world file, save it, and we're going to use some porcelain commands to speed ourselves up here. So I'm just going to do a git add, do a git commit. Also, a really terrible commit message. Don't do this. And if you open up the branch file now, what happens is that you see that this new branch now points to that new commit. This is a new hash. And if you take a look at git log, you'll see that the top hash corresponds to the latest commit, and now it's chained to all of the preceding commits. So visually, it looks something like this. We changed a file, and we staged it, and then we committed it, which then creates a commit object and links it to the prior commit, and at the same time, moves the branch reference so that it now points at this new commit object. And if you wanted to check out master and get your master revision back, what would happen is that Git would read the master branch file, which would contain the commit hash. And from there, it would follow the chain of hashes through the trees until it gets to your relevant blob objects. And from there on, it unpacks those blobs into your working directory. And now you're probably wondering, how does Git know what branch we're currently working on? So that when we do a git commit, like we just did, how do we know what branch to move that commit to? And the answer is in the head file, which resides on the top level of the .git folder. And this is just a text file that points to the path of your branch, as you can see right there. So git log, git branch, along with a bunch of other commands that you run when you want info on your current branch, reads off of this file. So if you bring the head file into the picture, the diagram then starts to look like this. I ran out of space there. And when you do a checkout to another branch, under the hood, what's happening is that this head file is getting edited so that it points to another branch. And by the way, you've probably also seen the term detached head state floating around. What a funny term, right? It's a very memorable phrase. If you're wondering what that is, it's when you do a git checkout to a commit that no branch points to. So it just looked like that. That is a detached head. So anyway, the overarching point that I really want to drill in here is that branches are not some sort of fleshed out entity. Rather, they are literally just a text file with a pointer to a commit hash in it. And we do this because we need a human-readable and meaningful way to reference the commit object that we want to work off of. Because those 40 hex character hashes are seriously hard to remember, right? But we'll certainly remember something like master, or feature, which is, by the way, a terrible name for a branch. So one last topic, Git pack files. So I mentioned earlier that Git saves a copy of each version of your file, right? So if that is the case, then you might start thinking to yourself, geez, that would become pretty clunky pretty fast, right? I'm just going to show you. I'm just going to show the contents of our objects folder. And there you have it. This is the smallest repo ever, but it already has this many objects. How does this scale? So what I've been showing you so far is called loose objects. The thing is that Git sometimes automatically packs up these loose objects into a binary file called a pack file in order to save space and be more efficient. And it does this by using deltas. So we can manually reenact this process by using the git gc command. And the GC here stands for garbage collect. And with garbage collect, Git performs a rather complicated algorithm to determine which of these objects are similar. And then it picks a base to then make the delta, which is the differences between these objects, and stores that instead, which saves quite a bit of room. So before we run this command to start packing things up, let's run actually a git count objects on this to see what we have. So the H flag here represents human readable, and you see that we have a count of 11 loose objects for a total size of 44 kilobytes. And now, if we run a git gc, compress some things, run a git count objects on it again, just to get the stats. We now see that we have way fewer loose objects hanging around, and the total size has significantly shrunk. And if we do another sort of listing of our objects, it now looks different. So the pack file, the little guy on the last line, is the single file containing your deltas. And the index immediately above contains offsets into that pack file so that you can reference your objects pretty quickly. And if you run the plumbing command, verify pack, you'll see that all of the things have been packed up in your pack object. Copy the whole path, okay. There you go. So that's it for my portion on how Git saves space and manages to stay even more lightweight. And that actually also concludes my talk for how Git works. So I hope I've at least somewhat demystified Git for you, but really the best way to learn on this topic is to go in and dig for yourself. And so I wanted to share with you some of the resources I used in preparing this talk. The first item, Pro-Git by Scott Chacon and Ben Straub, is an amazing open source book, and you've probably actually seen it around online when you Google for some Git help. Personally, it is my Git Bible. And if you learned a lot from this talk, you'll learn even more from reading this source, because I've structured much of my talk and content around it, and drew from its really brilliant sort of explanatory approaches. So I'd like to give content to this. I'd like to give credit to this book as well. Another great perspective is on Git internals is Mary Rose Cook's Git from the Inside Out, and Josh Weagley, who explains Git from the bottom up. And a particularly great talk I found is by Matthew McCullough, if you're more of a video type learner. And lastly, I discovered this gorgeous, very recent blog post by Tyler Cipriani, which does a very thorough job visualizing Git's Merkle-DAG structure. And I wanted to thank everyone who helped me in preparing this talk by providing an audience for a dry run and offering feedback. And next, I wanted to thank all of you for being a great audience. And it looks like we're fresh out of time, so if you have any questions, I can't take them, but I'll be hanging around. You can ask me then. I'm very nice. Or feel free to tweet at me, and I'll respond there. So thank you very much.